this session, this afternoon session. The first speaker of this afternoon session is Kouichi Okunishi from the Niigata University. He is going to tell us about Lattice Unruh effect and word line entanglement for the XXZ chain. So please, Okunishi-san.
Yes, thank you very much. And I would like to thank everyone for coming. So I am one of organizers. I really hope that you can enjoy several interest talks and active discussions coming from a wide variety of research fields associated with quantum information. So my background is condensed matter theory and tensor network physics. And here I would like to tell you about some interesting connection between quantum spin chain physics, of course, in the condensed matter physics, and the Unruh effect, which is a very simple example of a gravitational effect on quantum field theory. So just a moment. So we should use pointer. Can you see? Oh, okay. So this work was done with a collaboration, done in collaboration with Dr. Seki, who performed a very tough quantum Monte simulation to estimate some entanglement entropy based on the entanglement Hamiltonian. So this this result was basically already published as this paper. So if you are interested in my talk, please see this paper later. So let me begin with my talk by showing this slide. This is a very famous Feynman's last blackboard at the occasion of his death. So what I want to concentrate on here is this part. So in this part, there are some physical topics listed. He was interested in at that time. So I pick up this part here, and you can see that there is the first topic is the Bethe ansatz problem here, with some arrow from the Kondo problem. Of course, Kondo impurity problem in the condensed matter can be exactly solved by the Bethe ansatz. And the second topic is a two-dimensional quantum Hall effect, of course, which is a prototype of the recent rapid development of the topological physics. And third one is here, Axel temp, which means that the Unruh effect, some thermalization of the vacuum observed by constantly accelerating observer. And I don't know what does this nonlinear classical hydro means, but anyway, in my talk, I want to explain some interesting relation between this Bethe ansatz problem and Unruh effect. And so the relation between Feynman and Bethe ansatz problem was reported by Oguri sensei at some Aspen colloquium. And you can find some slide at that time on the internet. So if you are interested in the interesting connection between the Feynman and Bethe ansatz problem, you can try the Google search with this keyword. even just now. So anyway, my topics is very closely related to the weight ansatz problem and Unruh effect. So of course, the quantum entanglement plays a very important role to understand physics of the quantum many-body systems. And now here, I want to concentrate on the spin chain problem. And we basically consider quantum spin chain with a sufficient long quantum spin chain, and then consider the bipartition entanglement problem. So we consider sufficiently, I basically consider the sufficiently long chain and divided it into the center of the chain. And by regarding the, for example, right half as a system part and the other part as a reservoir. And then by tracing out the reservoir part, and we consider so entanglement physics. So we consider the entanglement in the reduced density matrix describing the system part. And if you diagonalize the reduced density matrix, you can obtain some entanglement spectrum, or directly you can define some so-called entanglement Hamiltonian describing the system part of the entanglement. And interesting point is that this situation can be closely related to the tensor network physics, so-called density matrix renormalization group, which is one of the most typical tensor network algorithms based on the matrix product state. So of course, there are in the context of the ADS-CFT, there is another type of tensor network, such as Mera or tensor network renormalization. But here, I would like to concentrate on this simple situation, just a bipartition problem of the quantum speed chain, which is closely related to the DMRG or matrix product type, state type, tensor network system description. And here, my aim is for the integrable XXZ chain. We want to discuss analogy with the so-called Unruh effect, which is a very simple example of a gravitational effect on the quantum field theory. In order to consider this problem, the integrability of the XXZ chain plays very essential role. Then we can show that the entanglement Hamiltonian for the XXZ chain can be considered as a lattice version of the Lorentz boost operator by using corresponding 6-vertex model and related to the related corner transfer matrix approaches. By using this some well-known object in the classical lattice statistics, we can directly relate entanglement Hamiltonian of this system to the lattice Lorentz boost operator. And so by using this lattice Lorentz boost operator, we can directly discuss the analogy with the Unruh effect. And the another aim is our purpose is to using this correspondence. We try to visualize entanglement of the XXZ, bipartition entanglement of the XXZ chain with some classical world. Anyway, we visualize the entanglement of this system as some classical world lines of spins by using quantum Monte-Carlo simulation for the reduced density matrix. Because the reduced, of course, we are basically considering the ground state wave function of the XXZ chain. However, the resulting reduced density matrix in the system part is has a thermalized spectra. So we can simulate this reduced density matrix with some finite temperature calculation approaches, such as quantum Monte-Carlo simulation. And quantum Monte-Carlo simulation based on the world line algorithms provide some very impressive world line trajectory of the quantum spins, which provide a kind of visualization of the entanglement. So, oops, no. Okay, so but here I explain some basic properties of the so-called XXZ-chain. So let me start with some basic explanation of the XXZ spin chain. So the Hamiltonian of XXZ spin chain is given by this, and very usual nearest neighboring spin exchange type spin interaction. And important parameter is here, delta. This delta defines some spin interaction anisotropy. And if this delta have a sufficient large value, positive value, then a system is basically described by the classical Ising spins. Only the SZ interaction. So in this large delta regime, ground state wave function is basically a classical up-down type Nair order. This means that in delta infinity limit has no quantum correlation. So it means that the ground state wave function is described by just a product state. However, if delta becomes smaller, then effect of this XY term becomes relevant. As delta decreases from here to here, the influence of the quantum fluctuation gradually becomes large, and finally at delta equal 1, which is corresponds to the isotropic Heisenberg point, this quantum fluctuation totally destroys the classical Ising order. And if this delta is in this plus minus 1 regime, role of the quantum fluctuation becomes dominant, and system is basically in the gapless critical phase, which is often called Tomonaga-Rattinger rigid in the condensed matter theory. So, but here I want to concentrate on this Ising-like anisotropic regime, whose ground state is basically gapful. So ground state has an excitation gap, and correlation length, ground state correlation length is always finite in this pink regime, antiferromagnetic gapful regime. And for later convenience, we also introduce this parameterization in this regime. So this anisotropy parameter lambda is, as we will see soon, this parameter lambda is the effective temperature of the thermalization effect in the reduced density matrix. And a good point of this Ising-like XXZ chain is that this model can be exactly solved by the beta ansatz. So, for example, the ground state energy or some excitation gap or low energy excitation spectrum of this Hamiltonian can be exactly calculated by the beta ansatz. So as for this XXZ chain problem, we already know sufficiently the physics about condensed matter. Oh, oops. So as I mentioned, here we consider the bipartition entanglement of this XXZ chain problem. And we basically consider sufficiently long chain of the length 2L and divide total chain at the center of the chain and regard the left part as a reservoir. And so the system part is labeled by positive integer site index 1 to L. So then we calculate the ground state wave function of this chain and trace out the left part and construct the reduced density matrix rho. And if you calculate so rho log rho, you can obtain the bipartition entanglement entropy. And as I mentioned, this entanglement entropy or reduced density matrix of the one-dimensional problem can be easily calculated by the density matrix renormalization group, which provide usually numerically exact value of the entanglement entropy. And if you represent this reduced density matrix like this, this H is so-called entanglement Hamiltonian. Or and this is basically, I think, equivalent to the so-called modular Hamiltonian in the quantum field theory. But in the condensed matter community, this Hamiltonian is usually entanglement Hamiltonian. So, sorry. Okay. No. And in order to understand the structure of this reduced density matrix or entanglement Hamiltonian, the integrability of the XXZ chain plays a very important role. And here, I want to explain the connection of the XXZ chain and behind 6-vertex model, which is a 2-dimensional classical lattice statistical models like this. So here is a certain vertex, and the arrow configuration around certain vertex is determined. Then certain weight is of this vertex given by this configuration. So for the 6-vertex model, there are many lot of variety of the parameterization, but we here use this parameterization. And this lambda is related to the spin anisotropy parameter delta in the XXZ chain. But here U, there is another parameter U, which is called spectral parameter or rapidity are also included in this Boltzmann weight. And if you define in order to solve this problem, if you define the row-to-row transform matrix from this Boltzmann weight, this transform matrix also have this parameter U. And the important point of this 6-vertex model is that this transform matrix having another U prime commute. So this means that this transfer matrix U form one parameter commuting family of the transfer matrix. This means that this transfer matrix has an infinite number of the conserved quantities. Of course, in order to show this commutator, so-called Yang-Baxter equation of this Boltzmann weight plays very an essential role. And then the relation of this 6-vertex model and XXZ Hamiltonian can be straightforwardly given by this Baxter's formula. If you take this log and perform U derivative, it's reduced to the XXZ-chain Hamiltonian. And of course, original transfer matrix has a commuting family. So of course, so that the XXZ Hamiltonian H and transfer matrix T also commute. This means that the XXZ Hamiltonian and this transfer matrix has a simultaneous eigenstate. So by using this correspondence, we can straightforwardly represent the ground state wave function of the XXZ chain by using power method. There is a certain boundary state here, and if you multiply this state so many times, then finally you obtain the ground state wave function of the 6-vertex model here. So this means that this just corresponds to the path integral representation of the quantum Hamiltonian, ground state of the quantum Hamiltonian. So of course, XXZ-chain can be solved exactly by the Bethe-Anders. So we can formally write down the ground state wave function of the XXZ-chain in the Bethe form. But Bethe type wave function is written as some huge number of superposition of the plane waves. So in this sense, the Bethe type wave function, we can write down formally write down the Bethe type wave function, but it is almost useless to understand the ground state physics of the system. Instead, if you consider this type of if you use this type of the representation based on the classical 6-vertex model, we can see very, so how to say, very straightforward relation to the entanglement Hamiltonian or resistance matrix by using so-called Baxter's corner transform matrix. Baxter's corner transform matrix is defined as some quadrant of the 2-dimensional lattice of the 6-vertex model here. We divide this half infinite plane into 2 parts, which which correspond to the two corner so-called corner transfer matrix, having two different parameter, lambda minus u and u. So by using this corner transfer matrix, ground state wave function can be just written as like this. Two product of the corner transfer matrix correspond to the ground state wave function of the XXZ chain. Then a very, very essential consequence of the integrability is that if you the corner transfer matrix A, of course, this matrix itself has a very complicated form. However, because of the integrability, we can write this corner transfer matrix by using certain matrix, Hamiltonian-like matrix K in this form. And once we have this expression of the corner transfer matrix, the ground state wave function or resulting reduced density matrix, we can write the reduced density matrix like this. And here, beta lambda is defined as a 2 lambda because we multiplied a lambda minus u and a u, so the u dependencies disappear in this part. The effective temperature is determined by only the parameter, anisotropic parameter lambda. And of course, Z is just a normalization constant, like a partition function. Oops. And this entanglement Hamiltonian, or so-called corner Hamiltonian, has a very, very simple form, almost the same as the original XXZ Hamiltonian. However, here, N is inserted in front of the energy densities. So this corner Hamiltonian or entanglement Hamiltonian K has a non-uniform energy density, which increases in proportion with N. And the boundary condition of this entanglement Hamiltonian is basically free boundary. Of course, the N equal L point correspond to the original edge of the 2L spin chains. But this N equal 1 site is just a center of the original 2L chain. The left half has already traced out, but then some free type boundary condition, we assumed this N equal 1 edge. Of course, this problem is a finite size. For example, this is just a finite size chain, and here is a boundary. In this sense, this N equal 1 spin has should have a very strong boundary effect. However, this spin originally located in the center of the system. In order to reproduce the uniform ground state of the original spin chain, this small n region must be uniform even in this reduced density matrix. This means that at some special, very special temperature, beta lambda, boundary effect at n equal 1 site should be perfectly suppressed in order to reproduce this original uniform ground state. So there must be some mysterious magic in order to represent this Hamiltonian corner entanglement Hamiltonian represent reproduces the original uniform ground state wave function. Another important point is that the energy scale is of local energy scale is of course proportional to n here. So the temperature, effective temperature in the reduced density matrix is basically fixed at this value. So, however, this as U goes to the outer side of the system, this N also increases. This means that the effective local temperature at site N decreases as N increases. This means as U goes to the outer side of the system, effective temperature decreases, and so this is a possible source of the difficulty. This becomes a possible source of the difficulty in the later quantum Monte Carlo simulation, because QMC simulation is usually becomes difficult if temperature becomes low. So this is a basic observation for the corner Hamiltonian or the entanglement Hamiltonian generated by the 6-vertex model. In order to understand the more precise relation to the Unruh effect here, I very briefly explain what is the Unruh effect. So of course, this part will sound trivial for the gravity people, but maybe condensed matter people. I try to explain this this part for the condensed matter people. So what is the Unruh effect? Unruh effect is a kind of vacuum summarization. So we consider observer a constantly accelerating observer. Of course, the total vacuum ground state of the system is in the Minkowski frame is just vacuum, so single pure state. But if observer, constantly accelerating observer, which moves along this red line, and here is a light cone. So this if observer moving along this line, this observer cannot see the left half of the system. In the classical level, this right wedge and left wedge are totally disconnected, which means that classically these two regions are classically separable. However, in the quantum level, there is some quantum fluctuation, and this observer anyway can see the left hand side of this part. However, as this observer approaching to the right cone, this observer may feel some quantum fluctuation propagating from the left side. And this observer, feels this effect as some thermalized state with a special temperature, this beta. A is this acceleration constant. Which is called Unruh temperature. Of course, the system is Lorentz invariant. So if this A is 0, this is happen nothing. So, however, this frame is not already the so inertial system because anyway, this observer moving on this line can feel some quantum fluctuation or quantum entanglement of the left-hand side. This is so-called Unruh effect. And then, in order to understand the physics of this Unruh effect, important thing is that so-called Rindler-Fulling quantization. In order to understand observer living on this coordinate, we need to quantize the fields with using this frame psi and eta. Of course, original Hamiltonian of the Minkowski space is given by this. However, if you move to this psi and eta frame, the effective Hamiltonian or the Hamiltonian determining the time evolution, this eta is can be calculated like this. And important point is this K operator is K operator correspond to the Lorentz boost operator in the original Minkowski space-time. Quantize the field based on this eta psi coordinate. We can define the particles observed by the accelerating observer, which is denoted as B here. And this B operator provide effective reduced density matrix observed by this constantly accelerating observer. And this of course, this is of course the momentum space representation. But anyway, this Lorentz boost operator comes here at the shoulder of the exponential function with a Unruh temperature coefficient here. This is so-called Unruh effect. So oops. Now we go back to the problem of the quantum spin chain. The entanglement Hamiltonian for the XXZ chain is given by this entanglement Hamiltonian or corner Hamiltonian. And we can directly show that this corner Hamiltonian plays a role of the lattice Lorentz boost operator by using Yang-Baxter equation. If you sandwiches row-to-row transfer matrix here with a 2 corner transfer matrix, then this matrix, these two A minus mu causes translation of the parameter U plus nu. So in this sense, corner transfer matrix works as some rapidity shift operator for the background classical system. And from this relation, you can directly obtain this kind of commutator. P is an effective lattice version of the momentum operator, and H is a usual uniform Hamiltonian, and K is an entanglement Hamiltonian. of course, we are considering the lattice system. So commutator of the K and H does not go back to the P operator. This relation generates higher order conserved quantity. However, anyway, this K and P and H forms the lattice version of the Poincare algebra. So in this sense, the reduced density matrix in the of the XXZ Hamiltonian also described by a kind of Lorentz boost operator. So we can now see that, summarize that the relation between the quantum spin chain physics and original Unruh effect in the quantum field theory. For the original Unruh effect, the entanglement Hamiltonian describing the entanglement between the left Rindler wedge and right Windover wedge is described by the original Lorentz boost operator. For the case of the XXZ-chain, entanglement Hamiltonian corresponds to the corner Hamiltonian, which is nothing but a lattice version of the Lorentz boost operator, which causes some rapidity shift of the in the row-to-row transfer matrix. So we can now the clear correspondence between these two effects. So we can consider the entanglement of the XXZ chain problem as a kind of lattice version of the Unruh effect. This is my point. However, of course, there is a clear correspondence, but however, I also point out that some essential difference is also can be seen in this table. So for the case of the original Unruh effect, the acceleration constant A and mass gap of the quantum field are totally independent. So this A is just determined by some efficiency of your rocket. On the other hand, then for the XXZ chain case, this anisotropy parameter lambda, single parameter lambda, determines the effective Unruh temperature as well as the mass gap of the ground state wave function. In this sense, the lattice Unruh effect in the XXZ chain case, this anisotropy parameter, which of course this parameter controls the strength of the quantum fluctuation. If lambda is infinity, the system is totally classical. And if this lambda approaches to the lambda equal 0, then critical fluctuation devices fair and some quantum field transition may occur at the isotropy Heisenberg point. Then yes, Takayanagi-san.
So I'm very curious about this lattice have this relativistic lattice. I can understand if we have some critical point, we can have a conformal field theory and Lorentz theory.
Yeah.
Also. Yeah, imagine, but in your case is gapped phase.
So basically, now I am considering the gapped phase.
Very curious when you have such a Yes, yes. And in general, I think we have some only non-relativistic situation. And only special case, I expect some Lorentz symmetry.
Yeah.
So how can we, so is that because of your model have an integrability, or
yes,
how we can, so if we have some one spin chain model, and how can we distinguish this model has a Lorentz symmetry and other one don't have it?
Of course, this lattice Lorentz symmetry is heavily relying on the integrability of the XXZ chain. So if you add some non-integrable perturbation, this structure is totally broken.
I see.
So this clear correspondence can be only justified for the integrable case.
Then if integrability exists, then always do we have this Lorentz symmetry?
Exact lattice Lorentz symmetry must be broken.
Yeah, but if we have integrability.
Yeah, I think basically some kind of Lorentz boost symmetry should be maintained for the integrable case, I think.
Always.
I'm not sure, but as far as some corner transform matrix, explicit form of the corner transform matrix can be constructed, this kind of commutator must be generated by.
Thank you very much. That's very interesting.
So in this sense, for the XXZ chain case, some quantum fluctuation or the entanglement generate both of the acceleration constant and the mass gaps. In this sense, this example can be thought as some example of entanglement induced some geometry or acceleration constant A. So now we want to move to the numerical computation part. So in order to demonstrate the entanglement structure of the reduced density matrix of the entanglement Hamiltonian, we performed quantum multiple simulation based on the some world line type algorithm. World line type algorithm is based on formulated on the basis of the path integral representation of the lattice spins. For example, this red or green line represent spin up or spin down trajectory in the system. And then off-diagonal matrix element defines some scattering of the world lines, swapping type world lines. And classical SZ diagonal interaction term can be represented by this type of the diagram. So some bunching of the world lines. So in the present case, we are considering anti-ferromagnetic case. So this diagram becomes dominant in the low temperature region. And in the quantum multiple simulation, we stochastically update these world line configuration, and final approach is some thermal equilibrium state configuration, and then we perform numerical sampling of the physical quantities. And in order to draw the world line spin configuration, an important point is that the energy scale of the system is proportional to n. The usual quantum multiple for the usual quantum multiple simulation for the uniform system, we usually draw the world line on the cylinder-like plane. because of the reflecting the periodic boundary condition in the imaginary direction. But in this case, the energy scale of the energy scale is basically proportional to n. So this means that length of the world line also depend on the spin side. So in order to scale this n, we define this kind of angular time theta. We just scale original imaginary time tau with this a, which is defines effective acceleration constant in the XXZ-chain ground state. Then by scaling, with this scaling, we can draw the world lines on the with respect to this imaginary angular time, which moves from 0 to 2 pi. And then the world line configuration generated by quantum mechanical simulation can be illustrated like this. This green or red line shows up or down spin configuration. And this blue short radial line represent some swapping position of the two adjacent world lines. Of course, at this center of the site corresponding to the entangled point of the original spin chain problem. And as n becomes too large, here is the outer side of the original spin chain. But then an important point that density of this blue short line represent the strongest some amplitude of the quantum fluctuation. Because n becomes large, the effective temperature becomes low. So the number of the quantum fluctuation or this blue line increases. And near the center region, number of the kinks, blue line, is not so big. However, if you look at this overall structure of this world line configuration, you can see that the density of the blue line looks almost uniform. So this snapshot, of course, this is just a snapshot, so this contains some thermal fluctuation. But anyway, the overview of this figure shows that the density of the blue line becomes almost uniform near the center region. So in order to demonstrate this, we have plot the number of kinks or bond energy density. And if this beta star corresponds to the Unruh temperature, this green line, green symbol shows that the density of the kink or density of the energy becomes flat near the center region, which means that the quantum Monte Carlo simulation at finite temperature for the entanglement of Hamiltonian correctly reproduce the uniform ground state configuration of the original system near the center region. And we can actually calculate the usual spin-spin correlation function by using the quantum Monte simulation for the entanglement of Hamiltonian K. And we also calculate the spin-spin correlation function of ground state correlation function of the original uniform Hamiltonian H. And this result shows that both numerical computation perfectly in good agreement. with each other. This means that quantum Monte-Carlo simulation for K correctly reproduce the uniform ground state of the original spin system. So how much time is remaining?
5 minutes, including the discussion.
Okay. So I must hurry up. So we have now the explicit form of the reduced density matrix by using the entanglement Hamiltonian K. We can directly calculate the entanglement entropy of the original system as a thermal entropy for the entanglement Hamiltonian system. And now we have already performed the quantum Monte-Carlo simulation, so we can actually calculate this entanglement entropy as a thermal entropy for the corner Hamiltonian K. However, the estimation of the thermal entropy is still a very difficult problem in the framework of the quantum Monte-Carlo simulation, because we have to perform some numerical integration of the specific heat. And specific heat is very difficult to estimate in the quantum Monte-Carlo simulation. High temperature limit is basically okay, but we have to integrate this line of the specific heat down to the Unruh temperature. For the case of delta equal 2.0, Unruh temperature located around here, and anyway we have to perform this numerical integral of the specific heat to estimate the thermal entropy for the entanglement of Hamiltonian K. But anyway, we can do this by using some kind of Gaussian kernel fitting method with sufficient accuracy. And this is a result. This red symbol shows the result for the result of the quantum Monte-Carlo simulation. And as system size L increases, you can see that this symbol approaches to the exact value of the entanglement entropy. So in this sense, we can verify that the reduced density matrix based on the corner Hamiltonian correctly reproduce the entanglement entropy of the XXZ-chain ground state. So we can also define some detector of the entanglement in analogy with so-called Unruh-DeWitt detector. Unruh-DeWitt detector is a particle type detector moving along with this line. And this detector basically pick up some correlation function moving along this line, and which pick up some both Einstein type distribution of the thermal fluctuation. We can now consider spin system version of this detector, which can be defined by this operator. And the final result of the so-called angular time, some correlation function with respect to the angular time evolution is defined by this. And this we can anyway we can numerically calculate this quantity by using density matrix renormalization group rather than quantum Monte-Carlo simulation. And then the result can be seen in this panel. So the eta equals 0 corresponds to the just expectation value of the SG squared operator, and as eta increases. What? Okay. As eta increases, the value of this correlation function deviate from the classical value, and here is a you can feel maximal quantum fluctuation. And if you goes to the eta equal pi over a, this angular time correlation comes back to the classical value. So in the case of the lattice model, this kind of periodicity appear in the Unruh-DeWitt type spin analogy version of the Unruh-DeWitt detector. You can see this kind of periodicity. This is because of the spin system is living on the lattice. So my time is almost up, so I just put this summary slide here. So thank you very much.
Thank you very much for nice talk. So now we can accept questions. If you have any question or comment, please raise your hand. I have one naive question. So you showed that the result of the DMRG and the QMC for the entanglement Hamiltonian give us exact identical result. But can we obtain the additional information from the QMC, which cannot be obtained by DMRG?
Yes, the reason why I used quantum Monte-Carlo simulation is that anyway we wanted to draw this figure, so this is just a classical word line configuration. So this figure means that quantum entanglement can be represented as a thermal superposition of the classical word lines. If I use the DMRG, total entanglement is included in the some kind of matrix element of the reduced dense matrix. But I cannot pick up this kind of classical trajectory from the DMRG computation. But the most essential reason why I used the quantum Monte-Carlo simulation is just I want to generate this kind of classical trajectory. So in the sense of the in the level of the expectation values, I think that DMRG computation is much more efficient than the quantum Monte-Carlo simulation as far as this system is concerned.
Oh, okay, but by the way, what happened if you change the temperature from this beta lambda?
That's a good question. Of course, if you anyway, we perform quantum Monte-Carlo simulation. The temperature parameter beta is just a parameter. So if you set inverse temperature beta to the beta star, as I mentioned, you can reproduce the uniform ground state like this green line. But if you perform the quantum Monte-Carlo simulation deviating from this temperature, for example, here we tried beta Monte-Carlo simulation beta star times at the temperature for beta star then the uniformity around the n equals 0 center region of the system broken because of the some boundary effect appears in this blue symbols. Or if you decreases temperature, some deviation from the uniform line may appear here. This is because now we just draw the these one lines on the disk. But if temperature deviate from the Unruh temperature value, the total length of the world line becomes longer or shorter, depending on the temperature deviate from the higher or lower region. Then, in order to draw this kind of figure, you have to draw, if you, anyway, so if you try to draw this kind of world line at the temperature deviating from the Unruh temperature, you have to draw some world line on the cone like geometry. So then here appears some conical singularity.
Okay.
Sorry. This boundary effect reflects such a conical singularity of the world plane.
Okay.
If the temperature deviates from the Unruh temperature.
Okay, thank you very much. So Takayanagi-san, please.
Yeah, thank you very much for very interesting talk. So I have a question about the maybe different choice of subsystem when you define this modular Hamiltonian. So for example, your case, I think subsystem is semi-infinite line. Is it possible to have a result also for single interval, or maybe more difficult, but to double interval? About this
I think it's very difficult because my argument is heavily relying on this structure. So if you consider the double interval, we cannot use this kind of techniques straightforwardly. In such a case, we cannot like use this kind of naive exponentialized representation of the corner transfer matrix. So yes, I think it's basically it's very difficult. Other than
also, if we look at your expression of this entanglement Hamiltonian, you are putting some factor n. N is not just location of site. N times spin square as s square. And we can, I can just naively imagine that n, we can replace this n with any function of n. It's much like some changing metric of the background.
Yes, I
think
so.
Is it possible to also generalize your approach to some kind of, Hamiltonian curved space?
I think as an approximation, it's possible. But as far as the exact correspondence to the
I see.
integrability is concerned, it's very difficult, I think.
I see. Thank you very much.
Any other questions? If not, let's thank the speaker again. Next talk will start the 15. So we have about 4 minutes break. So
okay.
ランプさん、
聞こえますか？
聞こえ
Can you
ま
hear
す。
me? Okay.
Yes.
Let's start. よろしくお願いします。
よろしくお願いします。
よろしくお願いします。共同放送になると大丈夫ですね。じゃあスライドをシェア。
はい。
はい。
はい、今見えています。
はいはい。